Welcome to the second lecture in analog electronics. So in this lecture we are going to discuss the operating point of BJT and the factors affecting the stability of Q point. In the previous lecture we have already reviewed the operation of BJT. We are going to focus the common emitter configuration, and before we move into the Q point discussion, let us analyze the limits of operation of a transistor here. So this is the output characteristics of a transistor which is shown here. You can see there are limits imposed on the IC as well as VCE here. This ensure that the maximum ratings of the transistor are not exceeded. So the output signal exhibits minimum distortion if these limits are perfectly followed. So you can refer the specification of transistor or a specification sheet which is provided in Boylston for more information. So you can see the various parameters related to the transistor being described, and its maximum values or rated values will be given in the data sheet. You can refer that. It is given in section 3.8 of the Boylston, the book I have shared with you. And here you can see the maximum IC is the continuous collector current. That term is also known as continuous collector current, and its value for a particular transistor is given as 50 milliampere. This is as per a particular data sheet. Then maximum VCE, or this VCE value, is the the breakdown common emitter voltage. That is, beyond this VCE max, the transistor may go to breakdown. The reverse bias if it is increased beyond this VCE max. Then VCE SAT is giving you the saturation voltage, that is below this VCE SAT the transistor goes to saturation. And the maximum power dissipation, that is PCE, this is found out using VCE into IC, and this curve is showing the maximum power dissipation. Now this is the operating point on the curve with maximum power dissipation. It is given as 300 milliwatt. So you have to find out the voltage and current corresponding to that if you have the operating points. And the operating point should not go beyond this PC max. That is, power dissipation should not go beyond 300 megawatt. Now this is the basic amplifier circuit. The basic amplifier circuit, you can see what is an amplifier. It is used to amplify small voltage signal, or you want to improve the amplify the voltage as well as current of this particular signal, or power has to be amplified. Now here this small signal, this AC signal, is applied to the input of a common emitter connected transistor. This is an NPN transistor which is shown, and you can see the input, the biasing is done like this. VBB is connected, RB is connected in series with VBB. That is to limit, what is the function of RB here? To limit the base current, DC base current which is flowing. And the base current to the transistor will, if you connect an input signal here, this base current to the transistor will comprise of this DC current as well as the AC component of the signal. What is the function of this coupling capacitor CC1? This will ensure that only AC component of the signal comes to this junction, or only AC component is passed by the capacitor. This capacitor will block the DC. Now at the output side you can see VCC, which is a voltage connected across the collector to emitter, and this is reverse biasing. Okay, so this is reverse biasing the collector emitter junction, or effectively the collector base junction. And then you can see this RC value, the output is taken across this collector resistance RC. Again, you want an output which is AC signal. You want just the input what you are giving, you want it at the output in an amplified format, which means it should not have any DC component, or this CC2 will ensure that only the AC component of the output voltage is obtained at the output of the amplifier. So this all together is known as this coupling capacitor, then biasing circuit, all together forms the amplifier, the common emitter amplifier. Now you can uh, find out the performance of the amplifier, and for that you need to analyze what is DC load line. We'll see DC load line concept here. So DC load, what do you mean by DC load? You can see that the load output is taken across this particular resistance. Okay, so this load is considered to be the DC load. So for this analysis, you are taking the condition when no signal is applied to the amplifier. This circuit shows the quiescent condition when the input signal to the amplifier is zero. That is, this input signal is not there. That is zero, and only the DC voltages which are applied to the transistor to ensure active region of operation. That is very important. The active region of operation is ensured by this arrangement, so that when you apply a signal at its input, it will be effectively amplified by this particular circuit. Now here you can see this is in quiescent condition. VBB is applied voltage. RB is the resistance in series with VBB. And you have the VBE voltage across a base emitter. This is forward biased, which means the VBB voltage will be 0.7 volt or 0.3 volt depending on whether it is silicon transistor or germanium transistor. Now VCE, the voltage is the voltage across the collector to emitter junction, and collector across the collector and emitter. And here you see IC is the current that is flowing, the output current. So what is the equation for the emitter circuit? You can see it is VCC equal to IC RC plus VCE, applying Kirchhoff's voltage law in the collector circuit. So in the quiescent condition of amplifier, you get this expression. Now you simplify this expression or rearrange the terms, you get an expression in the form y is equal to mx plus c. What is this? This is the equation of a straight line. So the slope of the straight line, if you take IC as the y-axis variable, that is what is we are taking on the output characteristics. X-axis variable is VCE. You will get the slope of the line as minus 1 by RC, and the y-intercept as, this is the y-intercept C, which is VCC by RC. Okay. Now you observe it here, the DC load line on collector characteristics. So what is the significance of this DC load line? As you have seen in the previous circuit diagram, you see this load is output is taken across this. ICRC is the output which is taken. That is, here signal is 0, so you are observing here. So here what you can see is that the output voltage, when you take across RC, this is a non-linear device. This transistor is a non-linear device. It has its input and output characteristics which are non-linear. But the performance of this particular transistor is limited, or you can say that the external circuit is putting a constraint on the voltage and current. This external circuit, that is the component RC in the external circuit, is putting a constraint, so that in this nonlinear characteristic there is a limitation which is imposed by this. So in this quiescent condition, that fixing VCC and RC, okay, this VCC and RC, and finds out by fixing that we can see the operating point of the transistor, that is in the amplifier mode, and this operating point should lie on this particular DC load line. So how do we plot this DC load line? We got the y-intercept C as VCC by RC, and we got the slope as minus 1 by RC. So this theta will be tan inverse of minus 1 by RC. This is the slope M. Okay, so you got the slope, this theta, and you got the y-intercept, and what are the values when VCC is 0 and IC is 0? You can see that here. When VCC is 0, you see what is IC? when VCC is 0, you can see that, or sorry, when VCE is 0, you can see that IC is VCC by RC. You want to find out the value of IC. We have plotted IC versus VCE and you want to draw the load line. So you have to find out IC when VCE is 0, that is VCC by RC. So what is the value of VCE when IC is 0? When IC is 0, VCE is equal to VCC. From this expression, VCC equal to ICRC plus VCE. So here you can see this is VCE equal to VCC when IC is equal to 0, and this is VIC equal to VCC by RC, and that is a condition when VCE equal to 0. And joining these 2 points you get the DC load line. But we should know where exactly the operating point of a transistor must lie on the DC load line. For that, we have to apply Kirchhoff's voltage law to the base circuit, because that is determined by the base current. See, these characteristics are plotted for different values of base current. So where exactly the operating point must lie on the DC load line is determined by this base current. So how will you find out the base current? You know the value of VBB, you know RB, and VBE is, as I said, 0.7 or 0.3 volt depending upon the, it is forward biased condition. This base emitter junction is forward biased. Therefore, that is depending on whether it is silicon transistor or germanium transistor. And IB will be given by VBB minus VBE by RB. So if you get the value of IB, you can mark the operating point on the, or the Q point here. Now we can take an example to find out this. See, this is a silicon transistor and it is used in quiescent condition of common emitter amplifier with VCC equal to 12 volt, RC is equal to 1 kilo ohm, VBB equal to 10.7 volt and RB equal to 200 kilo ohm here. Here you can see. So we have to find out the operating point for this transistor, the silicon transistor, and for that we are given the output characteristics of this particular transistor. So here you can note one thing. The first we have to plot the DC load line. How will you plot the DC load line? The 2 points here on the y-axis and x-axis, if you know, you can easily draw the DC load line. So what are those points? The first point, the point here on the y-axis will be 0 VCC by RC. What is VCC in this question? It is 12 volt and RC is 1 kilo ohm. So with this you will get it as 0 and what is VCC by RC? It is 12 by 1000 or it is 12 milliampere. This is given in, IC is given in milliampere, or this is the point of on the y-axis. And what about the x-axis? It will be 0 VCC, isn't it? So that is 0 VCC means it is 0 and sorry, on the y-axis means it is it is VCC 0 and that will be 12 millivolt, sorry 12 volt and 0. This is in volts. So this will be the second point. So the load line will ultimately, if you draw a if you draw a straight line, you can see this is the DC load line. So you have drawn the DC load line between 0, 12 milliampere and 12, 0. So we should know the operating point is the load line where the transistor is operating in this quiescent condition. For that we should know the base current. How will you find out the base current? IB is equal to VBB minus VBE by RB. What is VBB in this question? 10.7 volt. What is VBE? It is silicon transistor, so it is 0.7 volt. And RB is given as 200 kilo ohm. If you substitute these values for BBB, VBE and RB, you will get it as IB as 50 microampere. So this is not given here. The 50 microampere condition is not, plot is not given here. So what you have to do is you have to plot the 50 ampere 50 microampere base current. For 50 microampere, the characteristic will be like this. In between this 60 and 40 microampere. So the intersection of this cara with, I can show it with some other color. So intersection of this cara with the load line of this 50 microampere cara with the load line gives the operating point of this transistor under this quiescent condition, that is when there is no input signal given. So this is the Q point. So the intersection point, this is the solution, this is the Q point, and this is IB equal to 50 microampere. Now, amplifier analysis using DC load line. So, a transistor can amplify AC signals only after its DC operating point is suitably fixed. We have fixed the DC operating point. So, this Q point should preferably lie in the middle point of the active region of the characteristics. Why? Because only then there will be faithful amplification without any distortion. Whatever input you give, you have to get an amplified version of this input at its output. There should not be any clipping of the waveform or any distortion of this waveform. Just we need the signal to be amplified. So for that, again consider this basic amplifier circuit. Now the quiescent condition is set. You know the operating point, and then you are applying this voltage signal at its input. We should see what happens to the output, whether it is amplified faithfully. For that, you can consider the same previous example, and you assume that you are applying a Vs is equal to 7 millivolt. That is the input signal RMS value, assume it to be 7 millivolt. So what will be the peak value? It will be approximately 10 millivolt. Or peak to peak variation. This if you know the RMS value, and if you know the this peak to be 10 millivolt, its RMS value is 7 millivolt, peak to peak variation will be this, peak to peak will be 20 millivolt. Okay. Now to the same previous example, you know VCC is 12 volt, RC is 1 kilo ohm, and VBB equal to 10.7 volt and RB is 200 kilo ohm. If there is 20 millivolt peak to peak variation, then assuming its input dynamic resistance, if you assume to be 1 kilo ohm for this common emitter transistor, then what will be the peak to peak variation of this base current? This IB will be delta IB, the peak to peak variation of base current will be given by this input voltage, that is 20 millivolt divided by 1 kilo ohm. Okay, so the base current peak to peak variation will be 20 millivolt by 1 kilo ohm, which will be 20 microampere. Okay, so this is IB equal to 50 microampere, and IB is going to vary. Why IB is going to vary? Because of this input signal. This input signal is varying between, it's an AC, so it is varying between 10 millivolt and minus 10 millivolt. So we are calculating if voltage is varying like this, how current will vary. Delta IB will vary. You will see a variation of 20 microampere here. Okay, if it is varying, that is 20 microampere change is there, then at this operating point 50 microampere, if you consider, there will be a 10 microampere increase from 50 and also a 10 microampere decrease from 50. So IB is going to vary between 60 microampere and 40 microampere. If so, what is going to happen here? This Q point will move between this point and this point. This is the Q point for 60 microampere. This is the Q point for 40 microampere, or the Q point is going to vary between these two points. So that is shown here. So in this figure, you can see the variation of IB. That is, operating point is moving between the 60 microampere and 40 microampere. So you are going to plot the IB current variation because of the input signal. That is what we are plotting. So IB, it is varying. It is 50 microampere for quiescent condition. That is, for DC condition, it is 50 microampere. So you are drawing a perpendicular to this DC load line, and that you are taking as at this zero of this quiescent point, and this we are going to take as the omega t axis. And with respect to omega t axis, we are assuming the variation is sinusoidal, since the input signal we are assuming to be sinusoidal, and the operating point is varying between the points A and B. So if you plot IB, you get a waveform like this. This IB is increasing from 50 microampere in the quiescent condition to 60, and then back to 40, and then back to 50, which is the quiescent condition. Now, since the operating point is varying, we can plot the collector current from these data. So, if you project it towards the left on the y-axis, you will get the value of the IC peak, IC variation. You can see because of the input signal variation, there is a variation in the IC also, isn't it? From the quiescent point. In the quiescent condition, IC is here. IC is here in the quiescent condition at the Q point. Now, because of the variation in the input signal, IC peak is varying between these 2 points. What are these points? It is 7.3 milliampere here. It is 7.3 milliampere. And this point, if you find out, it will be around 4.8 milliampere. So the operating condition here is IC is 7.3 milliampere, and the operating condition here is IC is 4.8 milliampere. What about the VCE voltages at these conditions? At this, you can see the VCE voltage is also varying, and it is varying between what are the values you can see? It is around 4.9 volt here, and this is around 7.1 volt here. Okay, so if you project, you can get the operating conditions of the transistor when this input signal is applied. This change in base current is occurring here. Okay, you can find out the current gain, voltage gain, and power gain of the amplifier from this data. What is current gain? If you can define current gain as delta IC, the change in collector current to the change in base current. What is the change in collector current? This 7.3 milliampere, and it is 4.8 milliampere. So I am writing it like this, the change in collector current. And what about the change in base current? It is changing from 60 microampere to 40 microampere. So it is 60 minus 40 into 10 raised to minus 6. It is microampere. So you get the current gain as around 125. This is the current gain of this particular common emitter amplifier. Okay, what about the voltage gain? Voltage gain will be, you can compute voltage gain from this expression, the change in collector to emitter voltage to the change in base to emitter voltage. What is that? Because of this input, you get a change as 7.1 minus 4.9. This is on the x-axis, you can see, divided by what is delta VBE? The change you got already, we have found out, it is 20 millivolt. 20 into 10 raised to minus 3. We discussed the input signal Vs, and we found out this as 20 millivolt, and from that only we calculated IB, isn't it? Change in IB. So this will give you a value of voltage gain of around 110. Okay, so this common emitter when we discussed why common emitter amplifier is widely used, I forgot to mention these points. It has significant current gain as well as voltage gain. Now what about the power gain? Output AC power by input AC power. We need to consider about the power gain. When you consider, we need to think about the signal only, isn't it? So for as far as the input signal is concerned, what is the output AC power ratio to input AC power? The output AC power will be IC into VCE divided by IB into VBE for this particular signal. What is that? What is that? This current gain into the voltage gain. Sorry, this is voltage gain, AV. What is the value? That will be 125 into 110, or this amplifier is offering a significant power gain of 13,000 750. That is why this common emitter finds application in amplifier circuits. It can offer significant power gain to the input signal. The next point, that is stabilization of this Q point. Why we need to stabilize the operating point, that concept will be dealt with in the second part of this lecture. Thank you.